Great. All right. Well, welcome everybody to today's meeting of the Western Hemisphere Virtual Symplectic Seminar. And we're happy to have Dahye Cho today from Stony Brook with a truly impressive title, Symplectic Criteria on Stratified Uniruledness of Affine Varieties and Applications to the Minimal Model Program.
Thank you. Thank you for introduction and invitation. So this is a result of my thesis under supervision of Professor McLean. And so today we are interested in certain non-compact symplectic manifold called completion of a Liouville domain. And Liouville domain is a compact symplectic manifold with boundary with exact symplectic two-form and Liouville vector field. That is transversely pointing outward along the boundary, and it induces a context structure on the boundary. Like for example, like complex consider polar coordinate in complex plane, and consider to form r times dr d theta. Then Liouville vector field is a half of r times d dr, and we see it's pointing outward on the unit disk.
So Dahye, we're still seeing your title slide. Do you mean us to be seeing?
Oh, really?
Okay, now we see the third slide. Yeah.
Yes. So I just explained Liouville domain. And can you see the next slide?
Yes.
So we will see Liouville domain like this, I like this picture. And so completion of Liouville domain is we attach half infinite cylinder that is a symplectization of contact boundary to so that we complete the Liouville flow like this, and consider Hamiltonian function on our completion of Liouville domain. That is C2 small inside interior of interior of Liouville domain, and like a linear at cylindrical end. And Hamiltonian vector field is omega dual of one form minus dh, and consider Hamiltonian periodic orbit. Like for example, given Hamiltonian with the slope lambda, then we see lambda times d theta is a Hamiltonian vector field, like this picture, and we see Hamiltonian periodic orbit like this picture. So Hamiltonian Floer cohomology is a Morse cohomology on the loop space of symplectic manifold, and the Morse function is symplectic action functional. Like, can you see my cursor? Like a Hamiltonian symplectic action functional is integrating like our primitive one form and integrate our Hamiltonian, and like the critical point of this action functional is exactly Hamiltonian orbit, and the gradient flow line is defined by this PDE called flow equation. And so the picture is our critical points are Hamiltonian orbit that and the flow the gradient flow lines are connecting flow trajectory. So for each Hamiltonian function, we define Hamiltonian flow cohomology and take a direct limit when we take a slope go to infinity, we get symplectic cohomology of completion of Liouville domain. And so it has a action filtration. The symplectic cochains have an action filtration, so that induce a long eject sequence, like from start symplectic cohomology with small action between minus epsilon to epsilon, and full action, and then the action, positive action that is consisting of non-constant orbits. And the action symplectic cohomology with small action actually isomorphic to cohomology of our M. So the delta, the connecting map delta actually show we have a Floer cylinder connecting non-constant orbit and constant orbit. Constant orbit corresponds to Morse critical point of interior of Liouville domain. So symplectic cohomology of completion of Liouville domain is our main tool, and we want to understand some property of algebraic variety. So let me remind some definition. So projective variety over complex number is uniruled if for a generic point X, there is a rational map passing through that point. And an affine variety is called C-uniruled if for a generic point X, there is a polynomial map from complex plane C to M passing through that point. For example, so when you blow up a point, the exceptional locus is like a exceptional locus contains a direction. Remember all the direction is it is a uniruled subvariety. So so in birational geometry, people want to understand variety up to birational equivalence. That is so variety are isomorphic away from divisors or subvarieties. And so Mori's minimal model program is kind of roughly speaking is a study of rational curves on a variety. I mean, the people want to find a minimal model. There is a canonical divisor is left, canonical shift, and like a very roughly speaking, they want to get rid of some rational curve that is a obstruction for a canonical divisor to be left, and after getting a minimal model, they want to classify them. So my goal in this project is using symplectic cohomology detect all the C-uniruled subvariety of affine variety. So goal is detect uniruled subvariety. So affine variety is a solution of system of polynomial equations, and we consider it as a like a example of Stein manifold or Weinstein manifold of finite type. And so affine variety has a compact affine variety M compactified to projective variety X with ample divisor like D. Then from that ample line bundle, from the choose a section of the line bundle and take a like a norm of the section and minus log of the norm of section and DDC give us the symplectic structure, and like we can show that actually like a affine variety is a completion of a Liouville domain, and the Liouville domain is a intersection of affine variety with a large radius for like embedded into Cn. So we want to detect all C-uniruled subvariety of given affine variety. And so question is, we want for each point we want to find a polynomial map passing through that. And how about like a weakened condition? How about can we detect holomorphic map satisfying Cauchy-Riemann equation? How about pseudo-holomorphic curve? But symplectic cohomology has a Floer cylinder. There is a perturbed Cauchy-Riemann equation. So
sorry, Dahye, can I ask you a question?
Yes. Yes.
Yeah, so I was just wondering, the last two slides, I was having trouble understanding the connection to the minimal model program, and I wonder if you could explain what that connection is.
Connection with
Yeah,
the minimal model program?
Yeah, like between the goal that you're describing here and the MMP that you put at the bottom of the slide before this one. I mean, I was assuming that there was supposed to be a connection, but maybe I'm wrong.
I mean, there is just my project is just inspired from minimal model program. We cannot detect like a minimal model program like consisting of a lot of like numerical condition, like so the minimal model, roughly speaking, we want is non-negatively. So people want to like get rid of some rational curve intersect with the canonical shift negatively, like very roughly speaking, like some numerical condition. And so I want to detect but my project is a little bit different from this idea. I just want to detect a uniruled subvariety inside of affine variety.
Okay.
So it's not that precisely detect minimal model, but like I want to detect a uniruled subvariety like inside of affine variety. But so far, like the symplectic cohomology had like a detect Floer cylinder. Like for example, from the long exact sequence of symplectic cohomology from action filtration. So this connecting delta map tells us there is a Floer cylinder connecting non-constant orbit and constant orbit. So so the main theorem says if a cohomology class omega, there is an image of delta, like some degree, then actually we can detect C-uniruled subvariety of complex dimension at least n minus k, and such uniruled subvariety actually like for any exhausting finite type Morse function on affine variety, it intersect the subvariety intersect with the unstable submanifold of the Morse function, like this is theoretically. So the idea is, so we have a Floer cylinder. So it is a perturbed Cauchy-Riemann. It satisfies perturbed Cauchy-Riemann equation. So we degenerate our Hamiltonian function constantly zero inside of Liouville domain. Then the bourgeois-Onceas Morse-Bot symplectic cohomology result show that so the flow cylinder actually, when you degenerate Hamiltonian constantly zero interior of Liouville domain, the flow cylinder deformed to J-holomorphic curve followed by Morse trajectory. So the picture like this. So we get a J-holomorphic curve intersect with the descending chain of Morse function, and we need another ingredient like the sandwich theorem. So for M, the M is a affine variety. M underbar is a Liouville domain, like intersecting with the large ball, and the M upper bar is a So the sandwich theorem says that affine variety has two Liouville domain, M underbar and M upper bar, and there is an exact symplectic embedding, and there are homotopy equivalent, and M underbar and M upper bar are Liouville deformation equivalent. Like a Liouville, like a primitive one form and conformally deformed, like a large. So from like this, we need so I need to draw this part. Let me explain the idea. So I cannot draw right now. So the next step is so we deform flow cylinder to J-holomorphic curve followed by intersecting with the descending chain of Morse function, and we put this picture into the family of affine variety, and that is actually Keller structure like a deformed. So, and then we take a limit along the family, we get a degenerate curve. So that is the idea of Mark McLean's called degeneration to the normal cone. Let me explain that part. So each fiber-wise rectangle mean this is a cartoon picture. This is like a P to the N. Consider we compactify affine variety M into X with divisor ample divisor D, and so X intersection with P to the N minus 1 is exactly the divisor. So the blue line is says the divisor, and consider P to the N times P1 and blow up. Can you see this? Blow up. So blow up 0 times P to the N minus 1. Then we project down. Then project down the first component. Then we have the fiber, fiber over 0 consisting of projective variety F and the exceptional divisor E. And the F minus E is isomorphic to the original affine variety M. And the clever way choosing some ample divisor. So this picture is when we restrict to when you restrict to P1 cross X blow up part, and only is like consider that projection. Each fiber is isomorphic to affine variety, original affine variety M. And each fiber, I'm not sure I can draw. I think I cannot draw like so. So like we made a family of affine variety, like each fiber isomorphic to affine variety M, but the symplectic they are symplectomorphic, but the Kähler structure degenerate to over the fiber over 0. But I need to draw another graph that each from the sandwich theorem, each fiber picture into one like a Liouville domain M upper bar, and each fiber like we have a holomorphic curve passing through a descending chain of Morse function, and that sent to reference Liouville domain M upper bar, and we get a sequence of holomorphic curve, like a and the boundary of the holomorphic curve is strictly outside of the Liouville aside of affine variety when it embed into a bigger Liouville domain. Then using, so we have a like even we have a holomorphic curve in each fiber, we consider it inside of a bigger Liouville domain M upper bar, and take a limit. Then so using a Joel-Fish's target local Gromov convergence, it means we carve out some outside of near the infinity, then we get a convergent, like a limit. So the limit over the fiber, limit inside of fiber over the 0 actually break into a rational curve intersecting with the descending chain of Morse function. So we get using degeneration to the normal curve, we get polynomial map from actually CP1, but CP1 minus point passing through intersect with Morse descending chain. And for each, so we get actually we can move our Morse function. Then we have a family of rational curve, and family of rational curve make a subvariety by Grossendi Hilbert scheme construction. So we get a Uniruledness subvariety, and so if cohomology class is a image of delta map of long exact sequence of symplectic cohomology, so we can find a Uniruledness subvariety like of dimension is like n minus k. Like we need to intersect with the Morse descending chain. And what is the meaning of stratified uniruledness subvariety? So we consider the union of such uniruledness subvariety for each image, or the cohomology class. So we define a measure L, that is the minimum degree of such cohomology class, that is an image of delta, that measures maximal codimension of uniruledness subvariety. For example, our convention use the for example, if L is a 2K or 2K plus 1, then affine variety admits n minus k dimensional family of like affine line, or uniruledness subvariety. So if L is 0 or 1, then our affine variety is uniruled. For example, if symplectic cohomology is vanishing, then so L is directly vanishing. And for another example is if global Hamiltonian circle action accelerate the orbit, so the index increase, and we take a direct limit of like a slope of the Hamiltonian function, then symplectic cohomology is vanishing. So we get uniruledness from there. Another, I think, and two property of L invariant is when we consider end connected sum of two Lubel domain, that is a one handle attach between two Lubel domain and extend completion, then symplectic cohomology actually of end connected sum is like a product of symplectic cohomology of M and N. But from that property, we get L invariant become a minimum of 2 L invariant. And using Queen's formula, you get the following proposition as well. And so one result is, so consider more generally Weinstein domain. Let's start with the L of Weinstein manifold. Like infinity means none of its cohomology class hit by the delta map. So I put just infinity. So assume that we have a Weinstein manifold, then we can attach Weinstein K handle. So the length of cohomology strictly bigger than before. Then we get the L invariant after attaching Weinstein K handle become K. So if after attaching Weinstein K handle symplectomorphic to an affine variety, then we can detect uniruledness variety of dimension at least n minus k half and take a loop. And the idea is we use a chili box. Sorry, chili box result that subcritical Weinstein handle attachment does not change symplectic cohomology. So when you see this diagram, symplectic cohomology does not change, but cohomology change. So extra cohomology class should be hit by the delta map. So the L invariant become K. So we can apply this idea to yes.
Yeah, actually, I have a question about the theorem you're just talking about. Would you mind giving an example of such a W?
Like a C star. Is it? Like a C star to the n. Like,
Okay.
something has a lot of simplex, like a C star to the n, maybe. So like Weinstein handle attachment is like an interesting idea, and we have actually interesting like construction is a Kalima modification that is actually make affine variety into another affine variety. So which let M is a smooth affine variety and C is a irreducible divisor, and like a P is a closed subvariety that containing the smooth part of C intersect with M. And the Kalima modification of actually M minus C is a blow up M along P and delete the proper transformation of C intersection of M. So we blow up, delete the proper transformation of C. So amazingly, this is give us another affine variety, and interesting result of McLean is symplectic cohomology does not change. So if it change cohomology, then we get like a uniruled subvariety. Like for example, like actually I brought a C star cube. So consider divisor D inside of C cube defined by X times Y times C equals 0, and choose 2 points and blow up C cube at 2 points and delete the proper transform of the divisor. Then before Kalima modification, C cube might delete the divisor is C star cube, and the symplectic cohomology does not change. But when we blow up 2 points and delete the proper transformation, we actually have extra 2 cycles. So L invariant become 2. And using this idea, we can construct each dimension. Okay, we can have a affine variety with L measure equals 2, and like a product and some Q-ness formula. So and so another like a example I thought is cylindrical affine variety. That is a affine variety have dense Zariski open subset isomorphic to C times another affine variety, and by Quenet's formula, the open Zariski dense open part, symplectic cohomology vanishing. And so Zariski open dense open part has a symplectic vanishing symplectic cohomology. So my question is the original affine variety symplectic cohomology vanishing? So if at first I thought, are they like a I mean, maybe symplectic cohomology isomorphic. I think the answer is no, because consider M is like a complex plane C, and delete one point is a C star, so not isomorphic. So actually the result I had is yes, like a version of symplectic cohomology of cylindrical affine variety is vanishing, so we get C-uniruled. But the idea is actually we have like a spectral sequence from from symplectic cohomology after deleting divisor, and then converges to a symplectic cohomology of M. So let me explain the idea. We use actual relative symplectic cohomology of pair, like a compact subset inside of completion of Rubel domain. So, for example, like we will show that for like we will show like there is a spectral sequence from relative symplectic cohomology of like let me explain consider X projective variety X compactifying affine variety M with ample divisor like D1, and consider D2 is an effective ample divisor, like intersect with M is defined by polynomial F, and we want to show that there is a spectral sequence starting whose E1 page is a relative symplectic cohomology of X minus D1 union D2 with the like a symplectic structure from the divisor D1 union D2, and converges to relative symplectic cohomology of pair K inside of X minus D1. The symplectic structure is coming from ample divisor D1. So the idea is actually I show that there is two different symplectic structure, but they can be Weinstein homotopic. And then from this relative symplectic cohomology, so actually we use the filtration on symplectic code chain of this symplectic cohomology, and filtration by winding number along the D2. Like the winding number means we project our affine variety M down to C using the polynomial map F. Then so our like a orbits project down to C and count winding number along the origin. So so we get a spectral sequence, and then using small neighborhood of D2, boldface D2, actually does not can be stably displaceable. So this relative symplectic cohomology is isomorphic to relative symplectic cohomology of K inside of X minus D1. So this is idea of like the theorem. So we have a spectral sequence whose E1 page is a symplectic cohomology of M minus hypersurface that is vanishing. So the result symplectic cohomology is vanishing. So cylindrical affine variety has vanishing symplectic cohomology. So it's a C-uniruled. It's actually stronger than definition of uniruledness in algebraic geometry, because our uniruledness actually show for every point there is a polynomial map, like a C passing through the point even actually. So and so even though I cannot explain very precise like a meaning of our result in minimum model program, but I cannot like explain some part of like log minimum model program of affine threefold. So Kishimoto defined like a half point attachment to an affine variety. Like it is like a Kalima modification, but with the weighted, some weights. So half point attachment is like we blow, like a weighted blow up, 1,1b blow up, and then delete the proper transformation, like a very simply, like a speaking. So using the same idea.
Can I just check something?
Yes, yes.
So this gives you something singular when you do this?
Yes.
Yes.
Wait, like yeah, the very good question. When we weighted blow up, usually it's possible to get some singular thing. And like in general, minimal model program allows a mild singularity. But in our case, we simplify many things, like yeah. So like we assume like a colorable singularity happens at infinity, so we delete that. Like when you have, like when we do some half point attachment, so singular part will be deleted. When you delete that, yeah. And yes, so yeah. Then so it is the same idea of Kalima modification, but we have a like a weighted blow up, so we get we cannot get isomorphism after Kalima modification. We get isomorphism of symplectic cohomology, but this case we get spectral sequence from one to another. So the idea is, so affine variety M we consider is like A minus another, like divisor Y. M, so consider M is A minus Y, and half point attachment is M tilde. There is a blow up A and delete the proper transform of Y. But we can consider it as a M union of exceptional division. So we delete E. I think, yeah, delete E, so give us spectral sequence So the important part is our L invariant, like after, like before, like L invariant of affine variety before half point attachment is like greater than or equal to the after the half point attachment. So why this is important is like Kishimoto has a log minimal model program of affine threefold that is consisting of flops, some sequence of flops and divisorial contractions, but the flopping locus happening at infinity. So flopping does not affect to symplectic cohomology, and like then only like a divisorial contraction consisting of half point attachment. So, but we restrict our case to like a simpler, like some special case of Kishimoto's minimal model program, like with deleting hypersurface, like only the case. Then, like under special case, our like L measure are not decreasing along the minimal model program, like and yeah, I think yeah. And then like another thing is like if like a terminal object is not like isomorphic to the starting like affine threefold, then L measure is like L measure of the starting affine threefold is greater than or equal to 2, like a strictly change and detect some uniruledness from there. And so to summarize, from long exact sequence of symplectic cohomology of affine variety, we get stratified uniruledness of varieties, and some vanishing result gave us uniruledness, like a vanishing result under some like Hamiltonian circle action accelerating winding number of generating orbit, and invariance result from subcritical handle attachment and Kalima modification gave us some uniruledness of variety as well. And so deleting hypersurfaces, we get a spectral sequence that explains that like a cylindrical affine variety has a vanishing symplectic cohomology, and some part that explains some part of Kishimoto's like a log minimal model program for affine threefold. Like the interesting property I found is the monotonous behavior of L measure under certain affine birational morphism. So yeah, thank you. Thank you for listening.
Okay, let's give Dahye a hand. Any more questions for Dahye?
Can I ask again about this weighted blow-up?
Yes.
So I just didn't completely understand why you had the specific weights that you were using.
Specific weight 11B, you mean? I think
Yes.
Kishimoto used that like 11B. Is it like when he used like
Do you understand what happens topologically if you use different weights? I mean, can you do this analog of Kalman modification if you use different weights, or is it because somehow you want for there to be a unique singular point so that when you do the modification, the complement is smooth? I'm just trying to understand why this is the choice that makes sense.
Ah.
Right, because you did say that the
I think
modification
yeah.
is smooth, right?
Yes. I didn't think about that carefully, like, but that is a very interesting, like, a question, like, and more, yeah. Relate to yeah, weighted blow up. I thought about like understanding using symplectic cup, like but I don't know. I couldn't get any like a good idea, like to like apply.
Thank you.
Thank you. And any other questions?
So I was curious about the theorem that you stated on the cylindrical affine variety slide, this
Yes.
Sufficient condition for being C-uniruled. I was just curious if there were any examples of M that you found yet where it wasn't previously known whether they were uniruled, and this theorem lets you prove that.
You mean actually like a cylindrical, like a affine variety, like algebraic geometry, using algebraic geometry uniruledness, they are like immediately uniruled because they consider like a Zariski closure. Like if Zariski open part is a uniruled, then Zariski closure is uniruled. So, I mean, my like the theorem I had is different, like a more stronger uniruled, like for every point, like another Zariski closure of like some, like a generic. We don't need a generic condition. Like literally every point, we get a line.
I see.
So that is a difference. Like
Okay, thanks.
yeah, thank you. And I forgot like yeah, maybe I add a last slide, very last minute, like a slide. I don't know, this is I'm not sure this is a makes sense, like, or like from here is maybe just very vague thought, like people interested in like classifying like a minimal model, like, so we detect the uniruled subvariety, and we have a Ruby flow back to a skeleton, like, so I'm curious if a certain framed Lagrangian skeleton or spine of affine variety can be Weinstein homotopy to something simpler, like with arboreal singularity, like then can we like understand them? Can you classify them, or like can you understand like a birational morphism, like a flip, like for example, like this is a very diagonal like example, like for example, like a knot theory, like any link will not classified by finite number of like local moves. So like can you get a like a finite number of like a operation, so explain things, and like there is a and another question I have is can you like apply this idea to other version of symplectic cohomologies and get another like a uniruledness, not just a C. Or I don't know, some interesting subvarieties like that. Yeah. So that's it.
Okay, any more questions for Dahye? All right, let's give Dahye another hand.
Thank you.